This right here is our master fan remote prototype, something I've been building over the last week. Now this remote is designed to control multiple ceiling fans inside a temple hall. And in the actual temple premise, there are 16 fans in total, arranged neatly in 4 columns with 4 fans each spread across the hall. For this video though, we will demonstrate everything using our desk setup, just to clearly show how the system works. We'll walk through the hardware used, explain the basic connection diagram, and finally go through the program flow on the remote. So make sure you stay tuned till the end if you want to understand how this entire system comes together. Namaste and welcome back to Avinashee Tech. Now since this entire fan setup is inside a temple, shooting there requires proper permission and the right timing. So for now, we won't be showing the actual hall footage, but hopefully in a future video, we'll be able to bring you that as well. So what's the actual problem we are trying to solve here? Right now, each fan is controlled manually using ball switches. And the problem with switches is there's no proper speed control, no centralized control for fan or lights. During large gatherings, managing all these fans one by one becomes extremely inconvenient. On the other hand, if we go with standard RF-based fan controllers, each receiver comes with its own paired remote. So for 16 fans, that means 16 different remotes, which is honestly not practical at all. That's where this idea came from, to build a single master remote, a remote that can control all 16 fans efficiently from one central place in an organized way. So we are back at our desk with all the components we'll need to build this prototype. At the heart of the system, we are using an ESP32 board. For the display, there's an SSD1306 Oled which shows all the fan menus and submenus. For wireless control, we are using a 433 MHz RF transmitter and receiver. Based on the fan number and the selected option, the ESP32 sends different RF codes. Among the receivers, this small green RF module is the one that actually fits inside the ceiling fan canopy. For our transmitter module, we will be testing both helical and SMA antennas during the prototype phase, just to see what works best in terms of range and reliability. To navigate through the display UI, we are using a rotary encoder as our input device. And finally, everything will be assembled on a perf board. The OLED and ESP32 combo might look familiar because it comes straight from the LVGL video series here on this channel, where we went deep into the SSD1306 datasheet, discussed libraries in detail, and a lot more. If you haven't checked out those videos yet, I would really recommend watching them. It will give you a foundation before this project. Alright, back to our prototype. You can think of this video as a project wrap-up that brings everything together, from what we learned in the display tutorial series to now actually building something practical out of it. Now, let's take a look at the connection diagram. We will start with the rotary encoder. The CLK pin of the encoder is connected to D5 of the ESP32. The DT pin goes to D21 and the SW or switch pin is connected to D19. Next is the 433 MHz RF transmitter module. Its data pin is connected to D18 of the ESP32. Moving on to the OLED display, this is a 7-pin SPI based OLED module and the connections are as follows. CS pin is connected to D2, DC goes to D4, MOSI is connected to D13, CLK goes to D14, and finally the RST or reset pin is connected to D16. Now let's talk about powering the prototype. We are using 2 lithium-ion batteries connected in parallel to increase the current capacity. The positive terminal of the battery pack goes to Vin plus of the MT3608 DC to DC boost converter, and the negative terminal goes to Vin minus. The output of the boost converter is set to 5 volts, and from there Vout plus is connected to Vin pin of the ESP32, and ground is connected to ground as usual. All the peripheral components, the encoder, RF module, and OLED take power from the 3v3 pin of the ESP32 along with the common ground next to it. And finally, we have added a decoupling capacitor on the ESP32 module to help compensate for any voltage drop, especially during RF transmission. Alright, we have the components, we have the connection diagram. So next, I moved on to assembling all the components on a perf board or zero PCB, and this is how the final prototype looks. So everything is now set up. Let me open up VS Code and finally flash the updated esp-idf firmware with a few last minute tweaks. The firmware for this project is developed using the IDF platform, and the entire display handling is done using the LVGL graphics component. Enter the flash command, and there we go. The firmware is uploaded. At this stage, it's always a good idea to test different firmware use cases before actual deployment. This not only helps verify that everything is working as expected, but also allows us to observe the program flow in real time. Right at the startup, we see channel name appear on the screen. Next, we have a quick animation, an image sequence displayed fast enough to replicate a GIF-like behavior. This gives a nice, smooth transition before the main interface loads. After that, we land on the main display menu. Now in the firmware, there are two important tasks happening in parallel. One is updating the display, and the other is sending RF commands whenever required. On the main screen, we have a vertically scrollable menu listing all 16 fans. As I rotate the encoder, system detects the direction of rotation and converts it into up or down motion. And that's what allows us to move smoothly between the different fan entries. When I press the encoder button for a particular fan option, we enter a submenu dedicated to that fan. The display updates again, and now we see the control options, power, speed, and light. There's also a back option to return to the main fan list. Just like before, rotating the encoder lets us move up or down between these options. Right now, no RF commands are sent yet. We are just navigating the interface. This interface is designed to be simple, so that even someone who isn't very tech savvy can operate it comfortably. Now, let's go inside the power option. Here, the display updates once more and shows the most basic controls, on and off. Again, the encoder lets us move between these options. But this time, when we click to select, two things happen simultaneously. The display moves back to the fan's submenu, and at the same time, an RF command is sent either for power on or power off, depending on what we selected. In the speed option, things work slightly differently. Here we have a 6-level speed slider shown on the display. Rotating the encoder now scrolls horizontally through the speed levels on the bar indicator. Once the desired speed is selected, pressing the encoder button locks it in. After that, the display returns to the fan submenu, and an RF command is sent for that specific fan speed. Finally, under the light option, we have 3 different light modes along with a light off option. Just like before, selecting any option takes us back to the fan submenu and triggers the corresponding RF command. The actual effect of these light modes will obviously make a lot more sense if I show you them running on the real fan setup inside the temple hall. Alright, that completes our transmitting side. Now let's move to the receiving side. And to keep it simple, I'm using an Arduino Nano and the receiver module that's actually inside the fans themselves as informed earlier. This one's an extra receiver, so it's perfect for quick bench testing. It has the same basic pins, VDD and ground for power, and a data pin for receiving RF data. Let's open up the Arduino IDE and the serial monitor. Next, let me power up the transmitter fan remote prototype with our batteries and wait for the GIF to finish loading. Alright, now I will scroll through the fan options on the OLED. Select fan 8, enter its submenu, and turn the power on. There we go. We have received a 40-bit RF code on the monitor. Now, let's change the light option to ring. And there's a new code for that as well. Let me go back to the main menu and repeat this for fan 1. Power on. Okay, code received. Light set to ring. Code received. Now you can see there's a clear difference in the transmitted codes. Cool. Everything looks consistent and the RF transmission is working exactly as expected. So that was the practical demonstration of taking what we covered in our LVGL display series and turning it into a master remote, a simple, cost-effective engineering solution built for a real-world use case. I hope you liked this video. If you did, make sure to hit the like button, and if you haven't already, do subscribe the channel for more such practical tech builds and hands-on tutorials. We will meet again in the next video. Till then, keep learning, keep creating, and don't let that engineering spark fade away. This is Avinashee Tech signing off.